the same topic, semiconductor, where I left with. So, continue with p-n junction. What is the application of p-n junction? You can convert AC to DC current. Okay, AC to DC current, the current flow and voltage regulation. Because by p-n junction, the current flow is always unidirectional. That is the application of p-n junction. Why need to learn? You must understand first. We need to learn p-n junction is used as a diode. p-n junction is a diode. Now we will go for that how we will make it. We have taken a block of germanium. A small piece of indium is kept on the surface of the germanium block. Then we are applying 500 degrees centigrade heat. That will melt and flow. The indium will melt and flow. It will go through some of the germanium also will melt at this temperature, and there will be mixture of germanium and indium. So on the surface there will be some indium left with some amount of germanium indium mixture and some germanium pure. So three things will be there. Okay, that is the diode. So just read out that we take a small piece of indium on the surface of germanium, apply 500 degree temperature, then indium as well as germanium some portion will melt. They mix together at this temperature, and then we get three things: indium germanium mixture and pure germanium. So all the three things are there. Okay, so first you are making it. After that, the heat is withdrawn. Just the heat is withdrawn. Automatically it will be cooled down and will be frozen like this. And we get three things: indium germanium mixture and germanium. Germanium is tetravalent, but indium is trivalent. So it will form a p-type. Now this p-type, this indium germanium mixture will be p-type, but the germanium itself here is n-type. Okay, because here electron is the carrier, n-type. So n-type and p-type together is forming the diode. That is called the diode. When n-type and p-type both are there side by side, that's called a diode. So you get a diode. And what is the purpose of a diode? Unidirectional current flow, voltage regulation, and apart from that we have AC to DC current converter. Okay, that is the application. AC to DC current converter. See the point number 2. The indium and some of the germanium melt and mix. Then point number 3, it is frozen, and this diode is ready. Point number 4, as the process goes on, the remaining molten mixture becomes increasingly rich in indium. When all germanium has been redeposited after freezing, the remaining material appears an indium button that is on the top. Indium button, and you have the germanium indium mixture in the middle, and you have remaining portion with germanium pure. So all the three things will be there. Okay, so this portion where germanium and indium is mixed together will form a p-type semiconductor, and here you have the n-type, and n-type and p-type semiconductor side by side forming a p-n junction and a diode.
Hi there. This is the first in a series of 3 videos on semiconductors. In this first video, I'll give a simple explanation of semiconductor band theory. We look at intrinsic semiconductors, then move on to doping in order to form n-type and p-type semiconducting materials. So, first of all, we're going to look at the element silicon, although other semiconducting materials are available. Silicon has the symbol Si and an atomic number of 14. This means that silicon atoms contain 14 electrons. 2 in the first shell, 8 in the next, then 4 in the outer shell. We refer to these outer electrons as valence electrons. These are the electrons which can form chemical bonds. Now we'll simplify a model of the silicon atom to show only the 4 outer valence electrons which take part in bonding. In individual atoms, the electrons can only occupy discrete energy levels. The production of line emission spectra and line absorption spectra can be explained in terms of the electrons moving to different energy levels and either emitting or absorbing a photon, although that's covered in another lesson. When a large number of atoms come together to form a solid, the energy levels become reorganized into bands as the atoms interact. Each energy band actually consists of many closely spaced energy levels.
This one is called valence band and this is called conduction band. Valence band and conduction band. The band gap should be around 1 electron volt for semiconductor. For conductor it is 0. For semiconductor it is around 1 electron volt and for non-conductor it is 15 to 20 electron volt. আর আসো দরকার নেই বাড়ি চলে যাবে. Okay, so this is the thing.
See from the diagram on the left that all 4 of the silicon atoms' outer electrons form covalent bonds with the neighbouring atoms.
This silicon, tetravalent silicon, connected to other 4 silicon atom in surrounding. Just see here, this is the central silicon atom. It is attached to 4 other silicon atom because they all are tetravalent. Now, if you apply certain heat, then some of the bond will be broken and electron will displace itself from the position to the interstitial position of the molecule. Okay, so that is, this covalent bond is okay, strong, but is not that strong like carbon-carbon bond. Silicon-silicon bond is comparatively weaker. Why? Because silicon is large size. So covalent bond will not be that strong. Carbon-carbon bond is very strong, but silicon-silicon bond is not that strong. Anyway, so whenever we apply heat, some of the silicon bond will be broken in the crystal itself, and it will displace in the surrounding. It will go into the interstitial space. That is the reason it acts as a semiconductor, because some of the bond can be broken. If the bonds are very rigid, then it could not become a semiconductor. That will be non-conductor. But here some of the bond can be broken by some amount of heat supplied, and that electron is freely moving. When the bond is broken, it becomes free electron. So this electron is displacing, going into the interstitial spaces, positions, and then the electron can freely flow. And at this temperature, a bit high temperature, maybe 100 degrees or so. So this is act as a semiconductor. Now, this electron, why need that much of temperature? Because silicon is 1.1 electron volt band gap. Germany, if you take, it will be easier because here the band gap is 0.7 electron volt. Instead of 1.1, it is 0.7 electron volt. That means the gap is smaller. That's why at a lower temperature also it will act as a semiconductor. Alright.
Now, out of interest, the diagram on the left shows what's known as the semiconductor bonding model. At 0 Kelvin, all of the outer electrons are bonded. The diagram on the right shows the energy band model. In order to explain the electrical properties of semiconductors, we only need to consider 2 energy bands, the valence band and the conduction band. These are separated by a band gap, which we'll discuss later. What I've not mentioned yet is that this is an undoped semiconductor of pure silicon, what we call an intrinsic semiconductor. As I said before, at 0 Kelvin, all the outer electrons are bonded.
So this pure one is called intrinsic semiconductor. Alright.
Let's look at what happens when we add some heat.
We are applying heat so that the bond can be broken.
The electron has gained enough energy to break the covalent bond and is now free to take part in conduction, meaning that the resistance of the material is reduced. The absence of the negatively charged electron in this position leaves behind a net positive charge, which we call a hole. In terms of energy bands, the electron, which was initially in the valence band, jumps to the conduction band, leaving behind a hole in the valence band. The band gap, or energy gap, is just the energy required for the electron to break the covalent bond and jump into the conduction band. As the semiconductor is further heated, more covalent bonds bonds are broken, resulting in more electrons jumping to the conduction band, with more positive holes created in the valence band. So as the temperature of a semiconductor increases, its resistance decreases due to the motion of the electrons in the conduction band and holes in the valence band. If we look at the diagram on the left, we can see that electrons from neighbouring atoms can move to fill a hole, leaving behind a hole in their previous position. Although strictly this was caused by the motion of negative electrons from left to right, we can also describe it as the motion of positive holes from right to left. Next, we'll look at energy bands in a little more detail. As I said before, we only need to consider the valence band and the conduction band in order to explain the electrical properties of semiconductors, and for that matter, conductors and insulators. Remember then that in order for a material to conduct, it must have electrons which are free to move within its conduction band or holes in its valence band.
See, for a conduction here, in case of a conductor, the conduction band and valence band are merged together. Okay, and it will be partially filled. Some portion is filled and some portion is empty. But here it is insulator, the gap is very large, 15 electron volt, 16 electron volt, is like that. And conduction band and valence band, there is a small band gap for semiconductor, like 0.7 electron volt, 1 electron volt, 1.1 electron volt. So in general it is called around 1 electron volt, the band gap. And here the band gap is 15 to 20 electron volt, and here the band gap is 0. Because there is no gap, actually they are merging together, and some of the portions are filled and some are empty. So easily electron can freely flow. And another thing to mention, when the silicon and germanium were applying heat, it is not only that electron is moving, but the hole is also moving. Hole is created and then the hole is moving, because the electron is shifting from one position to another position, so in the vicinity, and as a result the hole is also shifting its position, as you have seen already.
Conduction can actually be explained by considering only the conduction band. The conduction band is only partially filled, so electrical conduction is permitted. Unlike a semiconductor though, increasing the temperature of a metal conductor will actually cause its resistance to increase. This is because the number of electrons within the conduction band increases so much that they have less freedom of movement. Remember that in a conductor, the highest occupied energy band, the conduction band, is not completely full. In insulators, there's a very large band gap between the top of the valence band and the bottom of the conduction band. At 0 Kelvin, the valence band is completely full and the conduction band is completely empty. At higher temperatures, electrons don't normally gain enough energy to jump from the valence band to the conduction band. So with no electrons in the conduction band, conduction isn't possible. For an insulator then, the highest occupied energy band, the valence band, is full. Finally,
now another thing to mention, in case of conductor, metallic conductor, if you apply heat, the resistance increases, that you know. Resistance increases when we apply heat for a conductor. Why it is so? Because the different levels are all merged together, and when you apply heat, the electron becomes random. So movement is random, up and down goes on. So if it is irregular way, up and down goes on, then there is not a current flow in unidirectional way. There is a random way the electron movement is occurring, and that's why the resistance increases rather. But in case of semiconductor, if we raise the temperature, the resistance decreases, because some of the electron from the valence band will be promoted to the conduction band, and then the resistance decreases. Okay, so resistance decreases at a higher temperature for a semiconductor, but resistance increases for a conductor. And non-conductor or insulator, their temperature, whatever temperature we give, that is not giving much of conductivity. Okay, until and unless there is a state change or phase change, there cannot be current flow.
Semiconductors have a very narrow band gap between the valence band and the conduction band. Like insulators, at 0 Kelvin the valence band is completely full and the conduction band is completely empty. But since the band gap is so small, as temperature rises, some electrons can gain enough energy to jump from the valence band to the conduction band, leaving behind holes in the valence band. As temperature increases then, the resistance of the semiconductor is reduced. Next on the agenda is doping. Here on the left, we see the bonding model of an intrinsic semiconductor, silicon again. With the addition of impurity atoms during...
Now the effect of doping. Doping means mixing of some impurity. Impurity will reduce the resistance. Impurity will reduce the resistance. As you have already seen that if you give arsenic, contaminate arsenic into germanium, the arsenic is pentavalent and germanium is tetravalent. So one electron will be extra, and that electron will be called free electron, and free electron can easily move. Now, what is the effect of temperature on semiconductor? If we take the 0 Kelvin temperature, absolute 0 temperature, then semiconductor will become non-conductor, because all the electrons will be in that case at the valence cell. No electron will be there in the your conduction band. So all the electrons will be in the valence band, and nothing will be there in the conduction band. And in that case, the resistance will be quite high. But if we apply a bit higher temperature, higher than the absolute 0 Kelvin, then it will not happen. Hello? Sorry, class. So valence band and conduction band, here, that in case of semiconductor at the absolute 0, there is no current flow. But any other temperature higher than absolute 0, there will be current flow and resistance will decrease.
In the manufacture of the semiconductor, we can reduce its resistance. This is done in one of two ways. By doping with a group 5 impurity atom, such as arsenic as shown here, we end up with an extra electron. The energy level of this fifth electron is within the band gap, just below the conduction band. The energy levels associated with the extra electrons are known as donor levels. Even at room temperature, most of these electrons will gain enough energy to jump into the conduction band, thus reducing the resistance of the semiconductor. We call this an N-type semiconductor, since the majority of conduction is due to the negative electrons within the conduction band. Remember that we previously discussed the heating of an intrinsic semiconductor. For each electron which jumped from the valence band to the conduction band, there was one hole left behind in the valence band. This meant that in an intrinsic semiconductor, electrons and holes exist in equal number. When we dope the semiconductor, however, this is no longer the case. In an N-type semiconductor, the majority charge carriers are electrons, and holes, which are still present due to the process described earlier, will be very much in the minority. Despite the majority charge carriers being negative electrons, an N-type semiconductor is still electrically neutral, since the impurity atom, arsenic in this case, will have an equal number of electrons and protons. Now let's look at the P-type semiconductors. This time the impurity atom, or dopant, is from group 3, so only 3 outer electrons are available for bonding with the surrounding silicon atoms. This results in a positive hole, as shown. The impurity atom in the diagram, in case you were wondering, is indium. The addition of group 3 impurity atoms leads to additional energy levels in the band gap, just above the valence band. These are known as acceptor levels. Electrons in the valence band require very little energy to move to the acceptor levels, leaving...
The main difference between N-type and P-type, you see, for N-type, just below the conduction band, there is another band created that is called donor band. And here, in case of P-type semiconductor, there is another band created, is called acceptor level, just above the valence band. But in both the cases, you can understand the gap is decreasing. As there is another band created, so the gap is decreasing. For N-type, the extra band is created here, and for P-type, the extra band is created here. And the name is different. For N-type, it is called donor level, and for P-type, it is called acceptor level. But whatever the cause may be, the gap is decreasing, and that's why the resistance is decreasing.
Behind holes in the valence band. This is where P-type semiconductors get their name, because the majority charge carriers are positive holes. Conduction in a P-type semiconductor is due to the motion of these positive holes within the valence band. Again, P-type semiconductors are electrically neutral, since the impurity atoms have an equal number of electrons and protons. So, that's us for now. In the next lesson, I'll be discussing the formation of a p-n junction and how it performs when forward or reverse biased. The third lesson will cover applications such as the LED and solar cell. Make sure to watch them too. For more information on upcoming videos, summary sheets and so on, visit physics-podcast.co.uk. Thank you for listening. Hi there, this is the second in the series of 3 videos on semiconductors. I'll be discussing the formation of a p-n junction and how it performs when forward or reverse biased. Applications such as the solar cell and light-emitting diode will be covered in the next lesson. Let's get started then. The diagram on the left shows a semiconductor crystal which is doped so that one side, the left-hand side, is p-type, and the other, the right-hand side, is n-type. Remember from the first video that the majority charge carriers in a p-type semiconductor are positive holes, and in an n-type semiconductor, the majority charge carriers are negative electrons. Despite this, both are electrically neutral. Where the p-type and n-type regions meet is known as a p-n junction. Here, electrons from the n-type material move across the junction and combine with holes from the p-type, and vice versa. This is a process known as diffusion.
From the n-type, free electron is moving into the p-type, and we are getting the p-n junction. P-type and n-type together kept just in good contact. There should be good amount of contact. Then the electron can flow from the n-type to the p-type, and you get the p-n junction. And what is the benefit of this p-n junction? It has got a lot of applications into practical field like photovoltaic cell, solar cell, etc.
Which creates a region within the semiconductor known as the depletion layer. The depletion layer is effectively an insulator due to the lack of majority charge carriers within it. The p-type region within the depletion layer now has a net negative charge.
The mixed region here is called the depletion layer. The mixed region where the n-type and p-type mix together, just like another example I have shown you, the indium button on the germanium that is mixed together, that portion is called depletion layer.
Due to the electrons diffusing into it from the n-type material. Similarly, the n-type region has a net positive charge due to the holes diffusing into it from the p-type material. Because of this, a potential difference is set up between the ends of the depletion layer, known as the junction voltage or potential barrier, which opposes the flow of further charges across the junction. In order for the p-n junction to conduct, this junction voltage must be overcome. Now let's turn our attention to the diagram on the right. Here we can see the energy band model of p-type semiconductor, where conduction is due to the motion of positive holes within the valence band, and n-type semiconductor, where conduction is due to the motion of negative electrons within the conduction band. When a p-n junction is formed, the energy bands warp like so. The region in the middle is the depletion layer. Fully explaining the energy band model of a p-n junction goes well beyond higher physics, so I'll not attempt it here. You can see though that the conduction band in the n-type has been lowered, and the valence band in the p-type has been raised. This is the electrical symbol for a p-n junction diode. We'll learn how it can be made to conduct when forward biased, but before that I should explain that this side, known as the cathode, is the n-type side, and this side, the anode, is the p-type side. Let's forward bias it. To do that, we can connect the negative terminal of a battery to the n-type side, and the positive terminal to the p-type side. This has the effect of narrowing the depletion layer, and if the forward bias voltage is greater than the junction voltage, then the p-n junction.
This semiconductor is connected to the power line in such a way. See, the P is connected to positive plate and the N is connected to the negative plate. Then this is called the forward bias. You can make the reverse one. This is connected to the positive plate and this is connected to the negative plate. That way it is called reverse bias.
Will conduct. When looking at the energy band model on the right, you've possibly noticed that when compared with the unbiased p-n junction, the slope in the depletion layer is reduced. This makes it easier for electrons to flow from n-type to p-type across the barrier, and similarly for holes to flow from p-type to n-type. So, when forward biased, electrons within the conduction band of the n-type semiconductor move toward the conduction band of the p-type. Holes within the valence band of the p-type also move toward the valence band of the n-type. Within the junction, electrons drop from the conduction band to the valence band and recombine with holes. Energy is released during these recombinations, and in a PN junction diode, this is in the form of heat, which results in a rise in temperature. To reverse bias the PN junction, we connect the negative terminal of a battery to the P-type side and the positive terminal to the N-type side. This has the effect of widening the depletion layer, and when looking at the energy band model on the right, the slope in the depletion layer is far steeper. When the PN junction is reverse biased like this, the depletion layer has become a greater barrier to the movement of electrons from N-type to P-type and holes from P-type to N-type. There's almost no conduction apart from a very small current known as the reverse leakage current due to the motion of minority charge carriers.
So in the forward bias there will be current flow, and the reverse bias there will be no current flow. So what is the purpose of PN junction? Unidirectional current flow. So AC to DC. See the application. See AC to DC. When it is coming in the forward bias, then current will flow, and the reverse bias condition, current will not flow. That means we can arrange in such a way we are getting current flow and not current flow. So that means it will become 1 and 0. So it will become bit. Bit and byte, you know, byte, megabyte, kilobyte. So that means our this computer chip, microprocessor, how it will work by based on this principle. This is the basic principle. Now there can be lot of modernization. That's a different thing. But the basic fundamental concept is this. Current will flow, you make it 1. Consider as 1. And current not flowing, so consider 0. So 1 and 0, that is the basic of the binary system. Bit, 1 and 0 is forming a bit. So accordingly you get 8 bit is giving a byte, then 1024 byte is giving a kilobyte, 2 to the power 8, like that. Anyway, so that is the thing. Let's continue.
The PN junction diode then displays asymmetric conductance. Don't worry, this isn't a term you have to learn. What it means though is that the PN junction diode has a high conductance when the current is in one direction when forward biased, and an extremely low conductance when current is in the opposite direction when reverse biased. This can be seen in the following graph of current against voltage. When forward biased, the supply voltage has to increase above the junction voltage before there's any noticeable increase in current as the forward biased PN junction conducts. When reverse biased, as mentioned earlier, the current is extremely small and the PN junction is effectively acting as an insulator. In the next video, we'll learn about applications of PN junctions, the light emitting diode and solar cell. That's us for now. For more information on upcoming videos, summary sheets and so on, visit physics-podcast.co.uk. Thank you for listening. Hi there. This is the third in a series of 3 videos on semiconductors. In it, I'll be talking about the light emitting diode and the solar cell, and how to explain their operation in terms of energy bands. Let's get started with the light emitting diode, or LED. The symbol for an LED is the same as the PN junction diode, except for one thing. These 2 arrows pointing outwards would signify the light being emitted or released. Now, we saw in the last video how a PN junction operates when forward biased. It's important to remember then that an LED is basically just a PN junction which emits light when forward biased. That is, when the negative terminal of a battery is connected to the N-type side and the positive terminal to the P-type side. Normally, LEDs are protected from large currents by placing a resistor in series with them, but I've not included that in this diagram.
Okay, I think you got sufficient idea whatever we need for this portion.